Hi, this video is going to cover logs, or I should say that the textbook covers some of it, videos in the book for Virtual Nerd, but so this is 7.3 in Algebra 2, and I'm going to cover mostly graphing log functions and a little more detail on what an inverse is and a little bit of detail on what a log is. But for the most part, there are a lot of videos on just converting logs and exponential functions, but not a lot on the graphing part. So I want to make sure we cover that. First of all, we know that if I have log base b of x, so that's how I say that, log base b of x, I guess y equals this. If I have this, I can go between, this is called log form, so I always have a base. Sometimes you won't see a base written there, and that is assumed a base of 10, and that's what your calculator also calculates, is base 10 only. So log, we can convert this. It's an if or only if, so there's the symbol for if or only if, so that means we can go back and forth. We can say the base to the y power equals x. So this is exponent or exponential form, hence the reason we're doing logs with exponents, they go together, okay? So exponent form, log form. And everyone's like, why do we do logs? We really use logs to solve very basic, even real life equations and functions. Even if you go to the bank and you're getting interest, you need a log function to tell you like how long it'll take you to get to $1 million in your account or whatever you're trying to get to. So logs are actually used in a lot of science and banking and different places. So like, why are we covering these log things? So we'll bounce between these two forms, log form, exponential form. So let's look at that. Here's an example. If I have 36 equals 6 to the second power. Well, we know this is true. We don't want to, we can see 36 equals 36, but we want to write it in log form. So what we're going to do is we're going to look the base of the exponent. I said that wrong. The base of the exponent is the same as the base of the log. So those are always going to be the same. So bases stay the same. That kind of helps with writing it in log form. So we're going to have log base 6. All right. Then from here, we want whatever it's equal to by itself to be right next to the log. So that's our 36, and it equals the power. So that's kind of how you switch between the two. So again, base stays the base, and then whatever you're equal to goes here, exponent here. Let's try a little bit harder one. So, okay, something like a fraction in there. So 8/27 equals 2/3 to the third. So the base of the power, or the exponent here, is 2/3. So we know we're going to go log of base 2/3 is equal to what's by itself goes here, and it's equal to the exponent. Okay, so there we go. That's converting from that direction. Now let's go the other way. What if I have log base 5 of 125? How can I write that in exponent form? Because a lot of times when I write something in exponent form, I can actually solve it, and it's a better way to go. So if we look at this, we can say, okay, 5 to what power equals 125? Base to what? So we could say this equals x. We have to make that part up, or equals y, and you could have a y here. I always use x. So when we just have a log, we're saying the base to what power will equal that number right by it. So you can actually solve these and keep going. And it does ask you to do that in quite a few of the questions. So what if we did want to solve this? So a lot of times we have to convert the log to an exponent form to be able to solve it. Sometimes we'll go the other way, but typically we go that direction. So let's see again how we solve these. I'm pretty sure we've covered this already. We need the same base. Well, we have 5 to the x. Can we write 125 to the base of 5? Well, you can. 5 to the third, I had to think about it, is 125. So I can write this as 5 to the x equals 5 to the third. And I can see that I can write them as the same base, so then I could just set the exponents equal to each other to get the answer. So x equals 3 is the answer. Not always do you have to solve. Sometimes you're just converting on some of the first questions you do in your homework, but some of them you have to solve. Let's do another one where we need to solve. Let me do one. Hold on. The other one that I picked is kind of hard, so I was like, well, maybe I want to do. Oh, I'll just do that. Log base 7 to the 7. So a lot of times we see a lot of them that end up with the same base and the number next to each other. The answer is always going to be 1, because 7 to what power would give you 7? It's going to be a 1. So x equals 1, because you know 7 to what power equals 7. So x equals 1. Another one that's similar that is kind of a little easier one is log base, I don't even care what the base is, of 0. Or not 0, 1. That's actually impossible, because 4 to no power will ever give you 0. 4 to the 0 gives you 1. So I was writing it wrong. You can't do logs of negatives, and you cannot do logs of 0. So you have a lot of things that aren't possible with logs. Here's what I meant to do. Anytime you have a 1 here, your answer will be 0, which is why I wrote 0. Because 4 to what power would equal 1? Doesn't matter what the base is. Any number to the 0 power equals 1. So anytime you have a 1 here, your answer will be 0. So these two are kind of like come up quite a few times, but they're a little bit easier ones. Okay, so then let's look at, that's our converting. Let's look at the next, let's see, maybe the graphing. Yeah, let's look at the graphing of them. So the graphing has the same kind of transformations we just did in the other section. So here's graphing logs. All right, so with transformations make logs a lot easier, and I'll show you why. So let's look at what a parent function would be for this one. Our parent function would be whatever the base is to the x. This is our parent function. And then when we add in the numbers again, remember those are going to move it up and down and all around. So let's look at it with the same letters we have been, just to kind of keep the same idea here. X minus h plus k. So here we go. We have our a timesing things by the log. We have our h that's inside by the x in the actual function. And we have our k outside. So remember the a, if a, we don't care if it's positive or a negative a, it is going to cause a stretch if it's greater than 1. So absolute value of a, meaning any positive or negative, if it's greater than 1, it is going to cause a vertical stretch. And that is a vertical. And again, your book doesn't use vertical. I'm going to in every single lecture. So the other one, oops, that's okay. So if you're in between 0 and 1, that means you're a fraction or a decimal, right? Between 0 and 1, it's going to be a compression. And these are vertical, so stretches you away from the x-axis. A compression mushes you, okay? And then h is going to be the horizontal, back and forth, translation. And then k is your vertical, up and down. And if you're just watching me write this, that means you should have been writing it. If a lot of students have not, they don't take notes. So if you take notes, then it's easier to be able to do your homework because you have notes to go with it, especially this kind of stuff. Let's look at a sample problem. What if I have y equals log base 4 of x minus 3 plus 4? So first of all, you'll be asked, like, what are the changes? So we can look at the changes based off of this, and then I want to show you how to graph it from there. So we can see there's no A, A is 1, right? Not no A, but A is 1. So there's not a stretch or compression because we didn't times it by anything. But we do have translations. This -3 is actually going to move you, remember, opposite. So it'll move you to the right 3. So from the parent function, we go to the right 3 and then up 4. Okay, those are the two translations we can see. Now it's pretty easy to graph the parent function, but this function without the transformations is tricky. And so let's look at what I mean by that. Let's do a little XY chart. And we're going to put in the parent function here. So remember, the parent function, you basically leave off the 3 and the 4. It's just going to be log base 4 of x. And that's it. And you could equals y, right? I can have the equals y on there. Sometimes I can't fit it in my little box, but that really could be there. So that is what we're looking to graph for our parent function. And we could convert the parent function pretty easy to exponent form because it's a little bit easier to see. So what would this look like as an exponent form? It would be 4 to the y power equals x. And that's our exponent form. Remember, those are the same thing. So sometimes, it depends on how you think, you might want to convert it because your calculator does not do log base 4. If your calculator did log base 4, it would be easier. I am going to show you a trick for that, though, in a second. But for now, let's look at numbers for this. What could I put in for y? I would put in a number for y and get out x. It's a little easier on this one because it's the same as thinking 4 to what power equals x. So I'm going to put in 0 first. So 4 to 0 is going to give you 1. And you could think of that as 4 to the 0 power has to equal, 1, right? So 4 to the 0 power has to equal 1. So I'm working backwards. Way easier. Think about 1. So we're going to have 4 to the 1 power equals 4. So I got 1, 4. Let's try a -1. What would we get? Now we can put a -1 in for an exponent, right? Or a -1 in for my answer. I couldn't have a negative where the x is, okay? I will not have a negative x. Because when I put in a -1 as the exponent, 4 to the -1, you flip it over and it becomes a 4th. That's how you're going to get fractions, and that'll help with your graph as well. So let's put in maybe, if I put in 2, 4 to the second is 16, so they get pretty large. Let's just leave it with those, and let's graph what we have here. Okay. So I have 1, 0, 1, 0. That's my first point, and then I have 4, 1, 2, 3, 4, 1. And I have 1/4, so over just a tiny bit and down 1, so 1/4 and -1. So here's what this graph is going to look like for this. Okay, it's going to be really close to going into that negative over here, but it never really will. So it has an asymptote here at the 0. So that's our general graph for this one with the base of 4. All of them look similar, base 10, base 4, base 3. It just depends on how quick it turns. But anyway, the number does affect it, but it's not much different. So this is a general graph of a log, but this is not the graph of this. What would this do? Well, you would take each of these points that we have and it would move them to the right 3 and up 4. So say this example, let's move this one. 1, 2, 3, 1, 2, 3, 4. So that's this point. So I can call this one big A, and I could call this one A with a little slash. So it's like the transformation or the image of it or whatever. So we can call this one B. We're at 1/4 -1. And so if I moved over 3, 1, 2, 3, and I moved up, up 4, right? 1, 2, 3, 4. I would be here. And then, let's see, 1, 2, 3. Yeah, and I don't want to cross the 3 because that's what makes 0 here, which we'll talk a little more about in a minute, but this would be B's moved. And let's call this one C. And then this one, we'd move it over 1, 2, 3, and up 1, so over 3, and then up 1, 2, 3, 4. And here's your new graph. Let's see if I can do this quite right. This one should not be touching the 3 mark. Okay, that wasn't the best, but that's okay. It's not the best drawing. That's all right. So we can see that it moved up, right? And we can see that it moved over. And that's the idea of using transformations. Okay, so transformations are really hard for a lot of people, and they really struggle with the idea. I can make a chart, and I can kind of think through this and just make points of this graph and graph it without thinking of transformations. So then you wouldn't have 2 full graphs to make. So let me show you what I mean. It still asks you about the transformations, but this is still the same question. I still have y equals log base 4 of, what did I have, x plus minus 3, plus 4. Okay, so I still have this. And what if I just want to graph this? I don't want to do the parent and then see what happens. Let's look. So we would still do our chart. XY, and in the middle we would have our log base 4 of x minus 3 plus 4. And here's how I want to go with this for you. I want you to think about numbers that would work for the 4 to the, how am I going to think of that? Okay, first of all, let's think of, we are only taking the log of this part. Okay, the plus 4 is after. So I want you to think about numbers in the x minus 3 that would work. It cannot be negative. So what would make, or 0, it can't be 0. So what would make 0 would be 3. So we know we cannot have 3 or anything less than it. So you can look at that little parenthesis and really think about, well, I can't have those numbers, so they're going to give me an error on my calculator. So I want maybe 1 is the first number I want to have, because I can, anytime I have a 1 here, the answer will be 0 in the log section. So what would make 1 right here? Well, it would be a 4. So I'm going to put in 4. So you have to think through these. You can't just put in 0, 1, 2, 3, 4 like you could when we graphed linears. It just doesn't work anymore. So let's figure out what we would have here. Then we'd have log base 4 of 4 minus 3, which is 1, plus 4. And I want you to think again, like do this part, then the plus 4. So this part here, just in itself, 4 to what power would give you 1? That would all change to a 0. So then I would really have 0 plus 4, which would give us 4. If we look at our graph, we graphed 4, 4 from before. Remember, this is our ugly one here. 1, 2, 3, 4. 1, 2, 3, 4. Ta-da, ta-da. We already have that point graphed, but here is another way for us to get it without doing the parent graph and the transformations. So then we have that. So we got a 1 in that parentheses. Now we want any power of 4s. So we want it to, let's make it a 4. What number would make it a 4 in that parentheses would be a 7. So I'm going to put that number in. So I'd have log base 4 of 7 minus 3 plus 4. Well, 7 minus 3 is 4. That's why we picked it. So what is log base 4 of 4 plus 4? What does this part convert to? 4 to what power is 4? It would be 1. Okay, so this would be 1 plus 4, which would give us 5. So here's another 0.75. That's also on our graph. All the way over to 7.5 was that next point where we turned. What if we wanted one of those fraction ones? Well, that's a lot harder. So if I want a 1, if I had a 1/4 here, I know I could get out a -1, because 4 to the -1 is a 4th. That would give us a fraction of whatever our base is. But this is kind of how off the grid here, how you have to think of that. Where x minus 3 equals 1/4, Oops, not 1/3, 1/4. So I would have to add 3 to it. So you basically just add the 3 over, and that's what number you're going to get, which is 3 1/4, which is the same as 13/4. Either way you want to think of it. So in order to get a fraction to kind of see where that asymptote will be, you need to put in, I always just do 1/4. If the base is 5, you do 1/5, and you have to see, usually you add or subtract that number to your fraction. So this, I'm going to put in 3 1/4. Okay, so I'd have log base 4 of 3 1/4 plus 4. Oh, 3 1/4 minus 3. Oops, minus 3. I was like, no, it doesn't. So what is 3 1/4 minus 3? Well, it's going to give us the fourth that we wanted. So we'd have log base 4 of 1/4 plus the 4. 4 to what power gives us that 1/4? That's our -1 that I was talking about. So I'd have -1 plus 4, which gives us a, yeah, 4. This is -1. -1 is a 3. Yeah, I for some reason think I didn't have that. No, I just didn't have that one on my graph. So I was like, that doesn't quite look right. But it makes sense now. Anyway, in my graph is kind of boo boo, but we can graph from exactly from these 3 points and we'd be fine. So our graph would look just like what we graphed on the other one. But this is a different way to think of it. I kind of like just doing them myself. But the translations are easier if you have the parent graph, and you could look at some technology for this, but I really want you to be able to do it by hand as well. I think you really truly won't understand logs until you've done quite a few problems with logs because they're so different thinking. One thing I want to point out is if you have something, this is called the change of base, and no, you're not taught this yet, but I want to point it out. Now, this is called change of base. So let's say I had log base 4, like my other problem, and I had something like 10, where I can't think of a number 4 to what power would be 10. I just can't come up with it. So maybe you put in a number that's not getting you out a number that is pretty. Here's how you can do that. It's called the change of base. You can actually, on your calculator, do log base 10, which is just what's on your calculator, of 10 divided by log base 10 of 4. So 10 fourths, 10 4, and you could put that in your calculator. So let me show you that. On this calculator, the log is here. Remember, I have to kind of slant it so you can see it. So I'm going to hit that log button, and I'm going to do it of, what did I say, 10? Yeah, 10, end your parenthesis, or you'll get the wrong answer, divided by log base, I had the base of 4, enter. There's the decimal. So sometimes they're not pretty, or sometimes you can't think of the number. You could use this change of base. So maybe you had the 5 and the 125, and you couldn't think of 5 to what power is 125. You could use this for something like that also, this idea of dividing your logs. And that again is called change of base. I just touched on it a little. So graphing with logs, I'm not going to do another example of it, but those are a little tricky. You can put in numbers or transform them all around. Okay, and then the next idea, this section really truly had, I thought, kind of some different ideas. Once you see this, I think you'll do your homework quick, but the video is probably going to take you longer. Then it had the idea of inverse. Now remember, an inverse is where I switch the x and y. That's what we do. We switch x and y, and typically then we would solve for the new y, and that's our inverse. So it kind of works that way with graphing, and they have a formula for it with that they give you at the beginning, where they say, okay, they tell you that y equals log base b of x is inverse is y equals b to the x. So that's the inverse of each other. I really didn't use that a lot to do graphs of inverse, nor did I really use it to solve, but I had never even seen it before, so I was like, maybe that's why I've never used it. But let's look at just doing an inverse of a log. What if I have y equals log, and let's do a little bit harder one, of x plus 12. Okay, so y equals log of x plus 12. What is the inverse? Well, what we do is we switch those x's and y's and we solve for the new y. So this will become x equals log base y plus 12, like this. And now we have to solve for that new y. Not quite as easy as it looks, but I would convert this now to exponent form. So I'm going to convert it to exponent form because you don't know how to solve anything with logs, and this, yeah, we really can't solve it this way, looking at it this way. So remember, if I don't have a base, it's a 10. So we have imaginary 10 there. So I'm going to say this is 10 to the power of x is going to equal, sorry, I lost my train of thought, y plus 12. I had written something wrong on my notes. I'm like, what? So 10 to the x equals whatever's here. Now I'm still trying to solve for y, so I'm going to minus that 12 over. So I'd have 10 to the x minus 12 equals y. So you can kind of look at this original idea, but I had a hard time with this what they give you for the formula kind of thing, and getting out this answer with that negative part in the 12. So we can see that the log base b to the x became, the base was 10, so we do have the 10 to the x. Where it gets tricky is if you have a number next to it. It becomes the opposite sign, minus 12 or plus 12 depending. But I think it's easier to switch them and think of it this way, because anytime I do any function, we did we have done exponential, excuse me, but we did quadratic, we did inverse, and you again switch the x and y and solve for the new y. Linear, you switch the x and y, solve for the y. I have a couple inverse questions on the final. I know it's easier to learn that process of that than it is going to be to memorize their formula. Okay, so switch x and y on your inverse. For graphing, you switch the x and y. So don't make the graphing harder than it is. What if I have y equals 10 to the x? What's its inverse? This one doesn't have a plus next to it. So I want you to find its inverse. That is going to be log base 10, which I don't have to write the 10, to the x equals y. Okay, so these are inverse of each other, and you can kind of see the same up here, bx, bx with the y. Okay? Okay. I keep saying okay. So graphing these, well, that's easier to look at in graphs, so let's graph that one first. Okay, so x, okay. How many okays did your teacher just say? All right, so x, put in 0. 10 to the 0 power is 1, so y would be 1, right? 10 to the 0. So what if I put in 1? So I'd have 10 to the 1, which gets me 10, which is going to get really big really fast. Let's put in a negative 1. 10 to the negative 1, what is 10 to the negative 1? 1/10 or 0.1. So 10 to the negative 1 flips it over and it becomes a tenth. And that's pretty much good enough. What will be the inverse without putting in numbers, which is still 10 to what power, which would be the y instead of the x, kind of idea, kind of switches, is equal to x. So this still, this would become 10 to the y equals the x. I mean, we could flip it back and say, okay, this one would be 10 to the y equals x for the inverse. And we could do our chart pretty easily. But another way to do your chart really easy on an inverse is, well, let's look at the first number on our own. If I put a number in for y, that's easier. So what if I put in 1 for y? Wait. 10 to the y equals x. It should switch every single point, so I'm thinking wrong. Okay, if I put in a 1 for the I did x, y, that's what I'm thinking of. Okay, so if I put in a 1 for the y, I would get out 10. So you can see that this one's the flip of this point. I was thinking it should have been this one, so I was throwing myself off. So I can see that if you just switch the points, I can recalculate them if I want. So if I put in a 0 for y, I better get out a 1. So this point went 0, 1, this point goes 1, 0. What will this one do? Well, if I put in a -1 for y, I get out 1/10 because 10 to the -1 is 1/10. So it flipped those as well. So let's look at that graph. So 0, 1, and then 1, 10. Oh, maybe I'll count a little slower than this because I have to go all the way up to 10. So we'll just do, this goes 1, 2. So the first one we're going to do 0, 1. I'm going to do it here. And then I'm going to count 1, then 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 110 is going to be here. And then -1, 1/10 will be like right here. Oops, -1, 1/10. Oops, right above, not -1/10. So, because it can't cross, it won't cross the negative here. So it goes really close, and then it goes up really fast because of the 10, like that. Okay, and that's this one, and its inverse is going to go 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1. 10, 1, 1, 0, 1/10, -1. So let's see here. There's that one. So there's our inverse. All right, so what do you notice about these inverse? They look similar, but one's kind of flipped over the other way. What an inverse does is this imaginary line cut down the middle this way, that's the y equals x line. Always the inverse is going to be the mirror image or the reflection from across that. So you can kind of fold your paper, imagine it in your brain, and they better line up from that crossing right out the middle. So don't make graphing harder than it is. You do one, flip them, done. That's all you have to do. You could switch it and calculate them out like I did. Either way is great. This is going to be a long video because logs are kind of challenging. There are still 2 videos in the virtual nerd that kind of cover more on logs if you're struggling. Also remember I do have some tutoring hours on Tuesdays and Thursdays. This semester. I'm in 2015. Just in case I use this video next year.